Very good morning and welcome to the lecture series session on EC 402 Nanoelectronics. My dear students, we have discussed about the formation and fabrication of nanofilms and nanoparticles in the second module. So in the third module, we will be discussing about the characterization of nanostructures and the characterization tools used for characterizing nanostructures. So what is meant by characterization? Characterization is actually the measurement of the thin film formed in nanostructures and their surface quality measurement. Any surface defect is there, nano defects are there, and what are all the chemical compositions involved, like so many kinds of information with regard to the deposition of nanoparticles and nanofilms on a sample surface that can be identified and that can be studied and that can be analyzed, and accordingly we can get the information with regard to the nanofilms or nanoparticles formed on surfaces of a substrate or material. So nanoparticles are more or less characterized in the same way as nanodefects or nanolayers. It requires sophisticated characterization tools developed from critical advancements in conventional characterization methods developed in bulk materials. So for bulk materials, we have different kinds of tools available to know the characterization both the chemical and physical properties and all. So when it is nanostructures, of course, the material is actually of nanometric level. So the characterization tool must be capable of measuring the properties of such materials in nanoscale with atomic resolutions. So we have to develop tools to know the characteristic features of both physical and chemical characteristic features. Okay, characterization and manipulation of individual nanostructures require not only extreme sensitivity and accuracy, but also atomic level resolution. I told you just now. The physical properties and short range of forces may have significant impact at the nanometric scale. That is physical properties and short range of forces. So I told you in the development of nanofilms and nanoparticles on surfaces, of course the surface will be always developing with certain kinds of energies on layers that we have already seen during the development of quantum dots, self-assembled techniques and all those things that we have seen. The physical properties and short range of forces which may have significant impact upon nanoscale. Okay, or at nanoscale. So characterization techniques in nanostructures can be classified as chemical characterization and structural characterization. These are the two basic characterization which requires for analysis in the case of nanomaterials or nanostructures. So we have to know the chemical characterization and we have to know the structural characterization. To know the size, shape, lattice constants and crystallinity of the material, structural characterization is done. I told you already that this particular characterization is actually done at atomic level because it is the material surface or material films or nanoparticles are actually on atomic level. Such a very minute particle structure it is having or lattice structure it is having. So to know the shape, size, lattice constant, crystallinity of the material, in order to know these parameters, we actually do structural characterizations. That is the structural characterization. To study the internal chemical structural details, the chemical characterization is done. So this is actually the chemical and structural characterization which usually done on nanostructures. So what are all the nanomaterial characterization tools? We will discuss some of the characterization tools and then we will develop gradually one by one. Okay. So first one, X-ray diffraction, XRD. X-ray diffraction has been widely used for what purpose? For knowing the crystalline character, crystallite size, crystal structures and lattice constant of nanoparticles, nanowires and thin films. X-ray diffraction technique is a characterization tool used for knowing crystalline character of the surface for the material, crystallite size of that film formed, or crystal structures and lattice constant of the nanoparticles or nanofilms or nanowires. Scanning electron microscope is another type of characterization tool, that is actually an electron microscopy and transmission electron microscopy, SEM and TEM, that together with electron diffraction have been commonly used in the characterization of nanoparticles to get an idea of size, shape and defects present in these materials. Usually, in order to know the size, shape and the nano defects on materials, usually we rely upon scanning electron microscopy, SEM, scanning electron microscopy and transmission electron microscopy, TEM. These are two electron microscopic methods or microscopic tools which are used for characterizing the nanoparticles in order to know the size, shape and defects present in the materials. Then optical spectroscopy is used to determine the size of the semiconductor quantum dots. In order to know the size of the quantum dots, we can rely upon optical spectroscopy. That's another tool, another characteristic tool or another characterization tool used in nanomaterials or nanostructures in order to know the quantum dot size of the semiconductor quantum dots. Then another type of characterization tool is actually the scanning probe microscopy. We have already seen, told about the scanning electron and transmission electron microscopy. Very similar to that one. Here there is scanning probe microscopy. It means that there is a probe, a scanning probe, which actually touches the surface upon which that nanomaterial films or coatings are there. And in order to know the characteristic features of such surfaces, this scanning probe microscopy is usually done. And in scanning probe microscopy, we have scanning tunneling microscopes and atomic force microscope. These are two microscopes, that is scanning tunneling microscope and atomic microscopes. These two microscopes are actually working with the principle of scanning probe microscopy, and they are very commonly used to know the topographic images of a surface. You know what is the topographic image? The topographic image of the surface, and that is done with atomic resolutions. I told you the material structure, the crystalline structure, and the topography of the surface. These are all actually of the order of that are all in the atomic level. So that is why, because it is in nanometers only, some 5 to 10 nanometers or so, such a very small size particles are there in nanometer under nanometer scale. So these particular uh, measurements have to be done, or the topographic images of the surface have to be done at atomic resolutions. At atomic resolution, the resolutions through which this particular material dimensions or the measurements are being done are having such a very accurate resolutions on atomic level. Okay. So topographic images of surface with atomic resolution in all three dimensions. In combination with appropriately designed attachments, this scanning tunneling microscope and atomic force microscope have found a much broader range of applications such as nano indentation, nanolithography, and patterned self-assembly. I think you have heard about nanolithography because we have discussed about this lithographic technique in the quantum dots formation, isn't it? Also, we have discussed about the patterned self-assembly. Self-assembly also we have seen in the formation of quantum dots, right? So, what is meant by nano indentation? Nano indentation is also another method of testing the nanostructures with for knowing its chemical and other properties or material properties of the or structural properties of the material, and that is actually done with the resolution on atomic scale. Okay, so that is what is called nano indentation. So nano indentation is very widely used in that is a surface thin film measurement of on nano scale. Actually that surface characterization and all those things which are done with the help of nano indentation. That is what is called nano indentation. So nano indentation testing is usually done on surfaces which are formed with nanoparticles or nanofilms. Okay, almost all solid surfaces, whether hard or soft, electrically conductive or not, can be studied with scanning tunneling microscope or atomic force microscope, because these two techniques of the microscope, that is scanning tunneling microscope and the atomic force microscope, that are all done under the scanning probe microscope. Okay, so these two type of microscopes can be used, whether the surfaces, that is specimens. Surfaces means solid specimens, whether it is hard or soft, electrically conductive or not, and the surface characterization can be done with the help of these two type of microscopy. In scanning electron microscope and tunneling electron microscope, this kind of things are not possible, because in scanning electron microscope, the sample must be a conductive sample. That is very important. Here, the sample cannot be always conductive in nature, or it should not be electrically conductive. You can use an insulator material to know its surface characterization. That is possible. So that is why STM and AFM has got that advantage, because it can be used for knowing the topographic information of the surfaces, whether the material surface is hard or soft, or whether it is electrically conductive or not. Okay. Surfaces can be studied in a gaseous medium such as air or vacuum or in liquid. So in this medium also, whether the surface is in a gaseous medium or a vacuum medium or in a liquid medium, so the surface characterization can be studied with the help of these two type of electron microscopes. Okay. Mm. So now we will discuss one by one about the characterization tools. First, we will discuss about the conventional microscope. What is the conventional microscope? Our conventional microscope is the optical microscope, isn't it? So optical microscope is actually used in order to know in order to study the material or its characterization when it is viewed, or when it is magnified, when the image is magnified to many times, isn't it? So that is the optical microscopy. So optical microscopy means we can have optical microscopy, which is a microscope, either it's a single microscope or a compound microscope. Both are possible with optical microscope. So microscopes are of three basic types: optical, electron, that is, or ion, electron microscope, ion microscope, both are usually called, but very commonly we term the name, or we actually call the name electron microscope. That is very widely used. And scanning probe. So optical microscopes are the, electron microscopes are the, and the third one is the scanning probe. I told you what are the scanning probe microscopes already. Now we will see one by one. Optical microscopes uses transparent lenses and visible light to enable viewing of the objects in the micrometer scale. So actually the optical microscopes can view images of the object on micrometer scale, that it can magnify the image to many times, but it is on micro scale range only. For example, red blood cells, human hair, or such type of, or cells of leaves, cells of leaves, for the study of cells of leaves. So such purposes we use optical microscopes. electron microscopes use electromagnetic or electrostatic lenses. So in optical microscope, of course, light is the main source of you know light is the main source to view the image of the object, isn't it? So here in electron microscope, the use of electromagnetic or electrostatic lenses are used instead of optical uh, lenses in the case of optical microscopes. Here in electron microscope, we use either electromagnetic lens or electrostatic lens. That you should always understand. Okay, optical lens used for optical microscope, but for electron microscope, where the main the source of image recognition is done with the help of electron beam electron beam, and this electron beam can be magnetic depending upon the so depending upon the beam characterization which is to be passed through an aperture. So what we do is we have uh, lenses which are electromagnetic or electrostatic lenses in the case of electron microscope. So in optical microscope we have optical lens. In electron microscope we have either electromagnetic or electrostatic lenses and a beam of charged particles, that is electrons. Instead of light we use charged particles in the form of a beam, that is the electron beam, and that is used for viewing the particle size of nanometer scale. So in order to know, in order to understand, in order to characterize, in order to see the surface of a material in nanometer scale, we use electron microscope which uses electromagnetic, electrostatic lenses and a beam of charged particles, and that is nothing but the beam of electrons from a source of electron in the electron microscope, and that is directed towards the sample surface in order to know its characteristic features on nanometer scale. So for nanometer scale, in order to characterize the surface or the surface of the nanomaterials, we use electron microscope. Okay, they have capability to magnify objects more than 500,000 times. See, 500,000 times this object can be magnified, the surface of the object can be magnified, thus allowing visualization of tiny structures such as DNA and microbes at a very high resolution. That is why electron microscopes are very widely used for knowing the surface characterization, to study the DNA and microbes on such a very small uh, microbes or such viruses. Sometimes study of viruses, bacteria, such type of things are usually studied with the help of electron microscope. Okay, and it is optical microscope. Now we will concern about the we will discuss about the optical microscope. It is a type of microscope that commonly uses visible light and a system of lenses to magnify images of small objects. Of course, this you might have studied in your 8th class, 9th class, and even the plus 2 classes. So I will just read something, and whenever there is anything to be clarified, that will be clarified. Otherwise, I will be just passing this one very easily, and we will concentrate on more on electron microscope because that has to be discussed in a wide way. Okay. So simple microscope is one that is single. That's the one lens microscope. That is simple microscope is one which uses single lens for magnification, such as a magnifying glass. So magnifying glass is a single microscope, and that is simple microscope actually because it uses a single lens. That is, it is called simple microscope. A magnifying glass is an example. And simple microscope works on the principle that when a tiny object is placed within its focus, a virtual and a magnified image of object is formed at the least distance of vision from the eye held close to the lens. That you know how the magnification is. But practically we use what type of microscope in optical microscope? A compound microscope. A compound microscope is the one which is very much familiar to know the microbes and all, isn't it? So that is to know the structures or images on micrometer level, micrometer range level. Okay. A compound microscope uses several lenses to enhance the magnification. In order to magnify the object, image of the object, there will be number of lenses used. Here, uh, this is the object A, B is the object, and this is the lens. This is the lens, and this is the optical center, and this is the focus F on either side of the optical center. And when you view from this one, of course, this is the object through which this is actually happening, and this line, that is OX, is going like this, and the line from A, that is passing through the optical center to Y. So this is a diverging rays, and that actually converges on the virtually on the side of this object AB, isn't it? So where it actually meets at the point A dash. So A dash B dash is the virtual image of this particular object. Okay. So now we will see how this is actually happening. A small object AB which is to be magnified is placed between the principal focus F and optical center of the convex lens. Now a ray of light AO parallel to the principal axis which is coming from the point A of the object passes through the focus F along the straight line OX after getting reflected by the convex lens. I told you this one, how this image, this virtual image is actually happened, or how it is, this particular virtual image is um, uh, produced, or it is actually the virtual image is created by viewing from this one, isn't it? That we have seen now. Now, um, so this is the simple magnifying glass. The image is here. This is the magnified view of the image of the object here. And this is a compound lens. Here we have used two lenses, isn't it? One is the eyepiece lens and there is the objective lens. So that if you are placing your object here, if you are placing your object here, sample here, then the rays are having like this, and you know the compound, how the compound lens create images. So the big magnified view of the image is taking place. So the image is a larger one, that is a virtual image, that we can see here. So here we get the image of this particular object in a very large and enlarged way. Okay. So this is the compound lens that I have shown you now. Now, compare optical microscope with electron microscope. This is an important question. Compare. Usually for 5 marks, a question may be asked like this. Compare optical microscope with electron microscope. How optical microscope is differing from electron microscope. So first we will see the illuminating source is light in the case of optical microscope. The illumination source is the beam of electrons in the case of electron microscope, isn't it? And specimen preparation takes usually a few minutes in the case of optical microscope, but in the case of electron microscope, it may take even few days, from many hours to few days. Usually. Specimen preparation for a electron microscope may take few hours to some few days, of course. It is used for the study of detailed gross internal structure of the surface of for the object. Here, this particular ultra microscope is used to study in the study of external surface, ultra internal structure of the cell, and a very small organisms. Usually, this is actually in the size of nanometric range or atomic range. Usually, it is used for knowing the surface studies and also the ultra internal, that is very deep internal structure of the cells and small organisms. Then here in optical microscope we can have live or dead specimen. Whether the specimen can be live or dead, that may be seen. And here in the case of optical electron microscope, only dead or dried specimens are seen. Here either dead or dried specimens are usually viewed and seen. Okay, that is the difference. Now, then optical microscope has condenser, objective and eyepiece lenses which are made up of glasses. But in electron microscope, all lenses are electromagnetic or electrostatics. Usually, the lenses used in electron microscope or electromagnetic microscope. In most of the cases, electromagnetic microscopes. There are certain microscope which can be used for diffraction of electrostatic diffraction also. So in that case, that is electrostatic lenses also used. Now, in electron microscope, we have low resolving power about 0.25 micrometer to 0.3 micrometer. But in the case of electron microscope, that is, it has got a high resolving power. Resolving power is of the order of 0.001 micrometer. 0.001. See, this is 0.25 micrometer. This is 0.0001 micrometer. About 250 times higher than the optical microscope. That is the resolution or resolving power. Then, in the optical microscope, we have the magnification of 500x to 1500x. But in the case of magnification of electron microscope, 100,000 to 300,000, such a large, very large magnification is possible with electron microscope. Okay. Then object is 5 micrometer or thicker. Here the object is 0.1 micrometer or thinner, even even thinner than this value. Okay. Then in the optical microscope, the image is colored. In the case of electron microscope, the image is black and white. That is another important thing here. Optical, it is colored image. Here it is black and white image. Then in the case of optical microscope, no vacuum is created or required. In the case of electron microscope, vacuum is very essential for its operation. That is an important thing. These are all very different thing with respect to the optical microscope. Okay. There is no need of high voltage electricity in the case of optical microscope, but in the case of electron microscope where electron beams are produced, isn't it? So that requires a very high electric current, electric voltage. So usually high voltage electric current is required. That is about 50,000 volts, 50 kilovolt. Such a high voltage is required in order to produce the electron beam. So that is why the operation of the electron microscope must be usually a trained personality can only operate an electron microscope. Okay. So there is no cooling system for optical microscope. Here there is cooling system. Why? Because we are actually directing an electron beam upon the surface of the sample. So naturally what happens due to the collision of this high energy electron, there will be heat produced, isn't it? So a heat and cooling system must be always there. That heat generated by high electric current must be that system must be that is actually that cooling must be provided for making the system in order to dissipate the heat, isn't it? Filament is not used in the case of optical microscope, but in the case of electron microscope, we have to produce what? We have to produce electron beam. So in order to produce electron beam, we require tungsten filament. So to produce electron beam, we have to use tungsten filament. Okay. Then radiation risk is absent in the case of optical microscope, but in the case of electron microscope, we have electron beams. So there is always a risk of radiation leakage, isn't it? So there is a risk of radiation leakage because we are actually dealing with electron beam. Okay. Specimen is stained by colored dyes. Specimen is stained by colored dyes. Here the specimen is coated with heavy metal that like molybdenum, gold or silver like, isn't it? So that we will see why we are using such type of uh, coating for the surfaces for the surface of the specimen which is tested. Specimen is coated with heavy metals in order to reflect electrons. Okay, so there should not be any static charges on the surface of the material. That is why it is coated with heavy material like gold, aluminum or molybdenum or such type of materials. Okay, platinum or such type of materials. The image is seen by eyes through ocular lens. Actually, the image is viewed with a ocular lens. That is uh, a optical lens. Here, in the case of uh, electron microscope, image is received in single sulfate fluorescent screen or photographic plate. Usually, it is this image is viewed on a fluorescent screen like zinc sulfate fluorescent screen, or it is received in a photographic screen or a computer monitor screen. Okay. Then we will see scanning electron microscopy. So we have seen the comparison of electron microscope and optical microscope. There are so many comparisons I have given, and you at least you remember about some 5 to 10 comparisons. Okay, so now we are going to learn about the characterization tools used for nanomaterials or nanostructures or surfaces produced with nanoparticles and nanofilms. Okay, the first electron microscope we have to discuss here is the scanning electron microscopy, SEM, scanning electron microscopy. A scanning electron microscope, so that is SEM, scans a focused electron beam over a surface to create an image. Understand this one. A scanning electron microscope scans a surface, isn't it? With the help of a focused electron beam to create an image. The electrons in the beam interact with sample, producing various signals that can be used to obtain information about the surface and the composition. So, over the surface, these electron beams are actually directed, and this beam interact with the sample surface, producing various signals. Usually, there will be different kinds of signals in the form of backscattered electrons, unscattered electrons, inelastic electrons, auger electrons, or sometimes X-ray diffraction electrons. So, different types of such signals will be produced, and that signals produced can be used to obtain the information with regard to the surface and the composition of the surface. Okay, the SEM consists of an electron gun to emit electrons that are focused into a beam with a very fine spot size of nearly 5 nanometers. So SEM consists of an electron gun, that is the basic uh, scanning tool, that is the electron gun, which produces electron beam. Okay, so that gun emits electrons that are focused into a beam with a very fine spot. This beam size is very small, of the order of nearly 5 nanometers, and such a beam is directed over the surface in order to study the composition and the characteristics behavior of the material over the surface. Electrons are accelerated to energy values in the range of few hundred electron volt to 50 electron volt. Some few hundred electrons, say some few hundreds of, say, from 500 electron volt to 50 kilo electron volt. Actually, this electrons are accelerated with the help of accelerating voltage to energy values in the range of some 500 electron volt to 50k electron volts, and which are rastered over the surface of specimen by deflection coils. Actually, this beam is actually rastered. Rastered means this beam is scanning over the surface. That is what is called the raster scanning over the surface. And you might have learned raster scanning in TV communication. Very similar to that one. Here also the beam is scanned over the surface and rastered over the surface of the specimen by deflection, and this rastering is taken place with the help of deflection coils. I will show you this one. This is the basic structure. Here this is the electron gun, and this electron gun produces electron beam, and that beam is flash sometimes, and in order to make the beam very narrow beam through this aperture, the spray aperture, we have the first condenser lens, very similar to the lens we use in the case of optical microscope. Here we have the electromagnetic lenses, and that lens will control the splashing of this beam, and that will be passing over this one and convert this through an aperture, that is the spray aperture. The beam spraying will be then converted through this aperture, and that comes to this area where the second condenser lens is there. Again, this beam is actually directed uh, and necessary deflections and all those things could be done with the help of this condenser lens, so that this beams comes through this one and reaches at the deflection coils here. Okay, so this is the deflection coils provided here, and this is actually the objective lens. What we have seen the compound lens, there is an objective lens, isn't it? So this is the objective, very similar to that one. This is also an electromagnetic lens that is called the objective lens, where this beam is narrowed and very clearly passed and directed towards the sample. This is the sample surface over which the characterization of the nanomaterial sprayed over this one, or nanofilms deposited over this surface is to be studied. Okay, so this beam is then directed over this one, and that is deflected with necessary deflection to this deflection coil, and that is finally reaches here, and this is the final lens aperture, and this objective lens will make necessary passage for this beam exactly flowing passing through this lens aperture, that final lens aperture, and reaching at the sample surface here. And here there are when it is reaching the sample surface, of course over the sample surface this high energy beam may create a lot of interactions. Such interactions may be an X-ray diffraction electrons, that may be an auger electrons produced, that may be a secondary emission electrons, there will be a backscattered electrons, there can be a inelastic electrons formation. So there are different types of specimen interactions takes place on the surface of the specimen in scanning electron microscope. Of course, we will learn what are all the important that interactions, specimen interactions are possible in SEM technique. Okay, so this beam is directed through this one with the help of this particular aperture, that is final lens aperture and deflection coils, and it is directed exactly over the surface. It can be controlled, so over the surface it reaches. And this, you see, this collimation of this beam, the collimated beam will be reaching here and finally narrowing, and the size is exactly 5, almost 5 nanometer size. That is falling over this, or impinging over this, or impacting over the surface. Okay, so it is high energy. That is also you have to understand. So here there are backscatter electron detector is there. There are secondary emission electron detector there. There are different kinds of secondary tools, or different types of measurement tools which are connected over this scanning electron microscope to know the secondary emission with the secondary electron detector, this backscatter electron with this backscatter electron detector. Likewise, there are different tools connected with this one in order to understand the different interactions made over this, or interactions occurring over the surface of the sample. And this particular this beam and the other all these things are kept on a vacuum environment. Actually, this is a vacuum chamber in which all these phenomena are taking place. Okay, that is what I have given here. And as the electrons strike and penetrate the surface, a number of interactions that result in the emission of electrons and photons from the sample occur, and SEM images are produced by collecting the emitted electrons. These emitted electrons due to the interactions, specimen interactions, are actually collected by different secondary instruments connected over the scanning electron microscope, and that is then passed connected to a cathode ray tube in order to see the visual display of the sample observed. Okay. A stream of monochromatic electrons are produced at the top of the column with the help of electron gun. I told you the electron gun will produce a stream of monochromatic electron beam. Okay. The electrons are accelerated down and is condensed by the first condenser lens. I told you this is the first condenser that is accelerating here, and that particular beam is accelerated and the beam is reaching, and then making it as a collimating beam and going through this aperture, the spray aperture here. Okay. The electrons that we interact with the sample that I have told easily. So the condenser lens not only forms the beam but also limits the amount of current in the beam. The condenser lens not only forms the beam, actually it accelerates the beam, and also which actually accelerates the beam but also limits the amount of current in the beam. Amount of current in the beam also is limited with the help of this condenser lens. The condenser lens together with the condenser aperture eliminates the high angle electrons from the beam. So whenever these electrons are coming out from this electron gun, there may have a chance of high angle beams to be produced, isn't it? So that is actually made a collimated beam like this with the help of this condenser lenses. Okay, with the help of this condenser lenses and the aperture. Okay. The condenser aperture restricts the beam and eliminates some high angle electrons. Actually, the aperture, the condenser lens that are all actually that are actually making the beam in a more directed way, which eliminates the high angle electron spreading. Okay, or high angle electrons. The second condenser lenses focus the electron into a thin, tight, coherent beam. Actually, second condenser lens again focuses this electron into a very thin, tight, coherent beam, and is usually controlled by the fine probe current knob. So there will be current knob provided on the that particular uh, scanning electron microscope panel. There will be a current controlling knob, a fine current controlling knob. So we can use that controlling knob to control the that beam current, control the beam current. Okay, an objective aperture further eliminates some high angle electrons from the beam. Objective aperture we have seen here. So this is the objective. There is an aperture that is final lens aperture, that is the objective aperture, and this is the objective lens, isn't it? So this is the objective aperture, and that actually does what? The objective aperture finally further eliminates some high angle electron from the beam. The position of the electron beam on the sample is controlled by scan coil. The position of the beam over the sample in order to fall the beam exactly over the sample, this deflection coils, actually there are deflection coils provided here. So here the deflection coil will be acting, this activate is acted, and that will always cause to make this collimated beam in order to direct it exactly over the surface with a very high energy. Okay. The position of the electron beam on the sample is controlled by scan coils that I told you. The final lens, that is the objective lens, focuses the beam on the desired part of the specimen. Wherever we want to examine the surface of the specimen, we direct that particular beam to that particular area. That is possible with this scanning electron microscope. Okay. So this is just to show how this gun crossover is coming. Gun produces um, electron beam, and that this is the first lens over which all the high angle electrons are avoided, and only through the aperture whatever is the beam which is coming through this one, that is the, actually converging here, and here it is, this is the lens 2, and here also we have the aperture, that is the final lens aperture, and from there this is the specimen surface over which this beam is actually falling over the specimen surface with a high energy, so that specimen interaction takes place. So there is specimen interaction takes place in this scanning electron microscope. Okay. Now, see, these are all some of the views I have made in order to see it very clearly. So, whenever this is the specimen surface, whenever these electron beams are impinging or there is falling over the surface, there will be secondary electrons due to the very high energy electron which falls upon the surface. So there may be emission of secondary electrons. There may be backscattered electrons formed. There may be X-rays, even X-ray diffraction. X-ray electrons will be formed. Of course, such type of X-rays may be formed. So there are different kinds of these kinds of interactions which takes place over the surface. Okay. So this is actually just to show the raster kind of specimens is scanned on rastered manner, means actually in the line by line manner it is scanned, and if you direct that particular area where it is scanned line by line, there is vertical ray trace, there is horizontal ray trace is there, so scanning line is here. So just to show how this raster scan is done on the fluorescent screen. Okay. Now, when the electron beam hits the surface of the sample, it penetrates the sample to a depth of few microns. Actually, when this beam hit over the surface, actually it penetrates the sample, isn't it? To some few microns, depending on the accelerating voltage and the density of the sample surface. The electron beam interact with the sample. They produce secondary electrons. So whenever this electron beam, which is having a very high energy, which is accelerated at a particular energy level, that will be falling upon, that will be hit the surface of the sample. Then what happens when it is hitting the surface of the sample? There may have different kinds of phenomena take place. What are those phenomena? They produce secondary electrons. That is called a secondary emission. They produce backscattered electrons. They may produce X-rays, and there are different kinds of such phenomena take place. And these phenomena are detected with various instruments. This phenomena can be detected in the various instruments provided on the scanning electron microscope. That is what I have shown you here already. Here there are different back scanner electron detector is there, secondary electron detector is there. There are so many, the X-ray detector is here. So there are so many other devices or instruments connected with this instrument, with this one, in order to give you the understanding of different phenomena takes place upon the sample surface. Before the beam moves to its next dwell point. What is meant by dwell point? So dwell point means when the beam hits over the surface, that is the dwell point at that particular instant. If the beam is uh, just or if the, that beam which is hitting on surface is moved to some other place of the surface of the sample, then the dwell point is next to the first one, isn't it? Before the beam moves to its next dwell point. Dwell point means wherever the beam is actually hitting upon the surface, that is the dwell point. These instruments count the number of interactions, and this instrument, what does it do? These instruments count the number of interactions and displays a pixel on a CRT, that is the raster screen available on the scanning electron microscope, the intensity of which is determined by this number. The more the reaction, the brighter the pixel. So it is actually available in the form of pixels, which is brighter if the reactions are more. Okay. The speed of scanning is such that the entire pattern can be scanned 30 times in a second. So the entire scan area could be scanned with the help of this beam about 30 times in a second. Okay. These signals are collected one by one or more collected one or more detectors. Actually, these signals are collected by these detectors and that are studied, which are then displayed on the computer screen. Okay, so these are all the specimen interactions which occur. This is the sample surface. This is the surface of sample. This is the sample. This is a wafer, maybe a gallium arsenide wafer or something like that, and over which the film on nanometric range is produced. And we are actually knowing, we want to know the characterization of the sample surface. What are all the thickness of the film? What are all the composition of the film? What are all the different defects possible? Or whether any defect is the nano defect is available there. Or different types of such characterization could be understood with the help of SEM. And when you just use the SEM for the purpose of knowing uh, all these interactions, or what is called the interactions which takes place when an electron beam is hitting the surface of the sample. Okay, so what are all the specimen interactions which takes place? I told you this is the electron probe and electron is hitting here at this point. This is the dwelling point. Okay, so there will be some electrons which may pass through this one without scattering. That is what's called unscattered electron. The electron which has got very high energy and that is capable of passing through this material surface is the unscattered electron, which is unscattered. There will be some electrons which will be penetrating through the sample and which may become inelastically scattered one. There may be elastically scattered electrons like this. And there may have X-ray emissions. There may have secondary electron emissions. There may have auger electron emissions. There may have backscattered electrons. So there may have the phenomena what is called cathode luminescence. Cathode luminescence. Then there are This is the interaction volume. So some of the area through which the interaction, the beam penetrates into the surface of the material or into the sample, we say. Okay. So for bulk thickness material, usually we use SEM because SEM will be hitting the surface and penetrating over the surface. That is the method of doing the scanning or analyzing the surface here. In the case of thin films, where we use TEM technique or transmission electron microscope, that we will discuss next. Okay. Now we will see what are all the specimen interactions take place. This is an important question. What is meant by specimen interaction in SEM technique, and what are all the important specimen interactions? What are all the important specimen interactions in SEM techniques? When the electron beam hits the surface of the specimen, various reactions can occur as shown in the diagram. I told you this is the diagram. Whenever this type of questions are asked, you have to draw this diagram. So this will give a good understanding about the different phenomena which takes place when the electron is hitting over the surface of the sample. Okay. Then some of the electrons penetrates through the specimen and interacts with it. The reactions noted on the top side of the diagram are utilized when examining thick or bulk specimen. The reactions noted on the top side of the diagram, that is here. Here I have made this. Here on the top side, the reactions made on the top side, that is bulk SEM. I told you that is for SEM bulk. The reactions noted on the top side of the diagram are utilized when examining thick or bulk specimen. If the specimen is a bulk specimen, we actually use SEM techniques, while the reactions on the bottom side are those examined in thin or foil specimens. If the specimen is a thin film or a foil, in such cases, of course, the reactions on the bottom side are those examined in the TEM technique, that is transmission electron microscope technique can be used. Just to understand that when a high energy primary electron interacts with an atom, it undergoes either inelastic scattering with atomic electrons or elastic scattering with atomic material. That is what is happening. When the energy transferred in the scattering is too large or it is large enough, the other electron will emit from the sample. When the energy transferred in scattering is large enough, the other electron will emit from the sample. So electrons will be emitting out from, because it's an electron with very high energy hitting over the surface. So that may cause to emit the electron from the surface of the sample. Okay. If the emitted electrons has energy of less than 50 electron volt, if the energy in such a way that the electrons which are actually emitted in such a manner that there are electrons which have an energy which is less than 50 electron volt, usually such a type of electron emissions are called secondary electrons, or electrons emitted from one of the orbitals of the incident atom. Okay, so that are all called secondary electrons. Since the secondary electron energy is small, the secondary emission images are highly sensitive to topographic variation. SC images means scanning electron microscope images. That is SC images. So that image will be very sensitive and to topographic variation. That is very sensitive to topography. If in what way it is recognized or identified, because if the secondary electrons which is having a small energy, because here the energy of the secondary electron emission is only less than 50 electron volt. If that is the case, the SC images are highly sensitive to topographic variations. Okay. What are backscattered electrons? Backscattered electrons are the high energy incident electrons that are elastically scattered and essentially possess nearly the same energy as the incident or primary electrons. So incident electrons, that is hitting over the surface of the sample. What is the incident electron? Incident electrons are the primary electrons which are actually coming out from the electron gun and accelerated by the accelerator condenser lenses that we have seen. So if that is the case, if such high energy electrons that are elastically scattered and essentially possess nearly the same energy as the incident or primary electrons. Usually, backscattered electrons, which actually emitted from the surface of the material, that is this sample, the backscattered electrons will be having high energy, and that will be always possessing an energy almost similar as that of the incident primary electrons. The probability of backscattering increases with the atomic number of the sample material. If the sample material is of a, a, a high atomic number material, then the probability of backscattering will be high. That is what does it mean. So it depends on the atomic number. Although backscattering images cannot be used for elemental identification, useful contrasts can be developed between regions of the specimen that differ widely in atomic numbers. So, depending upon the atomic number, if the atomic number is small, of course, the probability of backscattering will be less. If the atomic number is large, then probability of backscattering electron production on the hitting of electron beam upon the sample is more. That is the idea. Okay, that I think that you understand now. Hence, the backscattered electrons image can provide atomic number contrast in addition to the topographic contrast. So, there is a backscattered electron detector. Knowing the backscattered electron detector and their energy and all, this backscattered electron can give an understanding of the atomic number of the material which is deposited as film or nanoparticles over the surface, and that atomic number this particular device can measure, or this SEM can measure the atomic number contrast in addition, and that atomic number contrast, actually the atomic number can be understood, and if there is any change or there is any deviations from that one, that particular deviations could be, or that characteristic features could be understood with the help of knowing the backscatter electron detection and all those things. Okay, and in addition to that, when the topographic information of the images of the sample is also studied, and so that the topographic contrast, whether if there is any nano defects or whether there is any kind of variations over the surface, such topographic contrast could be identified and understood with this method due to the measurement of backscattered electrons and energy and all. Okay. Now, an additional electron interaction in SEM is that the primary electron collides with and ejects a core electron from an atom in the sample. The excited atom will decay to its ground state by emitting either a characteristic X-ray, that is photon, or an Auger electron, or both of which have been used for chemical characterization. So, this production of X-ray diffraction, X-ray photons and Auger electron photons, the X-ray photons and Auger electron emissions, that actually cause us to study the chemical characterization of the sample material. Okay, the excited atom, actually we have the electron beam directed upon a dwelling point where the atom will be excited, and there will be different kinds of interactions called the specimen interactions which takes place over the surface, and that excited atom will decay to its ground state. That will be decay to its ground state by emitting either as an X-ray photon or an Auger electron photon, Auger electron, not photon, the form that's an Auger electron, or both of which have this two type of um, that two type of emissions, that is X-ray photon or Auger electron emissions. Both have been used for chemical characterization of the material surface. Okay, the energy of the emitted characteristic X-ray or Auger electron are specific to the chemistry of the incident atom, and hence study of this can provide useful information on the chemistry of the sample investigated. So, the chemistry of the sample could be very easily understood with the help of X-ray emission produced by the hitting of the SEM beam, SEM electron beam, or by the production of Auger electrons and its characterization and those things. That will also give the idea of the chemistry of the incident atom, and hence study of the chemistry of the sample investigated. Okay. So, for chemical characterization, we can make use of these studies. What are all the amount of X-ray produced or X-ray photons produced, and what are all the auger electrons produced and their characterization and all those things. That will be giving you the understanding with regard to the chemical characterization of the material surface. Okay. Now we have to know the nature and preparation of specimen in SEM. So I told you this preparation of specimen is not simple in the case of electron microscope. In the case of optical microscope, it's quite simple. You can just adjust the that viewfinder and all those things. Visual that particular that light rays and the source of light rays and of course the lenses and all those things could be adjusted in such a manner that we can view it very easily and we can place the specimen in between and we can see the we can adjust the specimen in such a manner that it can be viewed very easily in an enlarged fashion, isn't it? In an enlarged or in a magnified way. But in the case of electron microscope, the specimen has to be prepared or the viewing of the specimen is not simple. It requires so many minutes or even hours to days in order to prepare the specimen. The specimen preparation is one of the most important steps in the process of imaging in electron microscopy. As the biomolecules and assemblies are prone to disintegration in vacuum under which the imaging is done. Okay, why we actually make this preparation of specimens? Because the biomolecules and assemblies which are prone to disintegration in vacuum. Actually, every activities, specimen interactions, all those things are done under a vacuum environment, isn't it? So, under this condition, disintegration of the biomolecules and assemblies which are taken place or disintegrated under vacuum condition. And under this vacuum condition only this imaging is being done. So for that purpose, we have to prepare the specimen accordingly. For SEM, the specimen must be electrically conductive. That is very important compared to other methods like AFM, atomic force microscope, or even scanning tunneling microscope, STM. Here in SEM, the specimen must be electrically conductive and that is to be grounded so that the charge, that is what's called the electrostatic charge. I told you at the time of explanation in the previous session that the specimen is usually covered with high metal like that is gold, molybdenum or platinum or so. So that is why is it done? This is the main reason for that. For SEM, the specimen must be electrically conductive and grounded so that the charge, that is electrostatic charge, doesn't accumulate at the surface of the specimen because the beam, the electron beam are actually hitting over the surface of the specimen. That is the film, nanofilm. So what happens since it is hitting at a very high energy? So usually there are chances to accumulate electrostatic charge over the surface. And if there is electrostatic charge over the surface, whatever measurement is being taken is erroneous. So what we do, we have to ground that electrostatic charge immediately as it occurs. Okay, that electrostatic charge accumulated over the surface of the specimen must be grounded. For doing that, what we do, the specimens are coated with conductive material like gold, palladium alloy, platinum, osmium alloy, iridium, tungsten, chromium, and graphite. The coating does not allow the static charges to accumulate on the specimen during electron irradiation. Electron irradiation means electron beam irradiation, electron beam which actually falls or which actually hits on the surface which is under examination. Okay, two important reasons for coating even when there is more than enough specimen conductivity to prevent charging or to maximize signals and improve spatial resolution. So while taking measurements, the measurements must be swing or there must be maximize the signal in order to get the good sample response. So in order to maximize the signals and improve the spatial resolution for the measurement, what we do, we have to use this coating of the specimen surface with the help of heavy metals like gold, palladium or copper because that actually causes to prevent the accumulation of charges. Not only that, Why, if the conductivity is there, even if the conductivity is there, enough conductivity is there, in order to get a very good sample signal and also to get the spatial resolution improved, we have to do this particular coating of the metal upon the surface, isn't it? So understood. I think you understood this one. The coating does not allow the static charges to accumulate on the specimen during the electron irradiation. Okay. The improvement in resolution arises due to the fact that in the case of low atomic number material such as carbon, the electron beam can penetrate several micrometers below the surface. For low atomic material, of course, what happens? So materials such as carbon, in which the electron beam can penetrate the surface several micrometers below the surface level. That generates signals from an interaction volume much larger than the beam diameter and reduce the spatial resolution. So when the penetration of this particular beam goes, which actually causes to penetrate several micrometers below the surface of the sample. If that is the case, what happens? The interaction volume much larger than the beam diameter may cause to reduce the spatial resolution. Coating with a high Z means atomic number. Coating with a high atomic number material such as gold maximizes the secondary electron field from which in from within surface layer of a few nanometers thick and suppresses secondary electrons generated at greater depth. So coating of this material, coating of either gold or aluminum, that actually maximizes the secondary electrons yield from the surface layer, and that electron yield from within surface layer of a few nanometers thick and suppresses secondary electrons. Actually, this coating may cause to suppress the secondary electrons generated at greater depths. Okay. Hence, the signal is predominantly derived from locations closer to the beam and closer to the specimen surfaces than in the case of an uncoated low atomic number material, especially relevant to the observation of biological samples. So, if you are just examining a biological sample, this is very important. The signal is predominantly derived from the locations closer to the beam, okay, and closer to the specimen surfaces than in the case of an uncoated low atomic number material, especially relevant to the observation of biological samples. So, if you are just observing the biological samples, what you have to do? The signal is predominantly derived from the locations closer to the beam. Actually, signal is actually closer to the beam. That means signal is actually derived from the electron beam and closer to the specimen, which actually hits over the surface beam, which is actually closer to the specimen surfaces than in the case of an uncoated low atomic number material, especially when the surface under test is a biological sample. So നമുക്ക് ലോ ആറ്റമിക് മെറ്റീരിയലിൻ്റെ ഈ പറഞ്ഞിരിക്കുന്നതായിട്ടുള്ള ക്യാരക്ടറൈസേഷൻ നടത്തുന്നതിനേക്കാൾ പിന്നെ ഇതായിരിക്കും ഇങ്ങനെ ബയോളജിക്കൽ സാമ്പിൾസ് ഒക്കെ നടത്തുമ്പോൾ ശ്രദ്ധിക്കേണ്ടത്. ഈ സ്പാഷ്യൽ റെസൊല്യൂഷൻ ഉണ്ടാവണമെന്നുണ്ടെങ്കിൽ നമുക്കവിടെ തീർച്ചയായിട്ടും സിഗ്നൽ ഇസ് പ്രിഡോമിനൻ്റ്ലി വളരെ അടുത്ത് തന്നെയാണ് സിഗ്നൽ, ഇലക്ട്രോൺ ബീം അവിടുന്ന് പ്രൊഡ്യൂസ് ചെയ്യുന്ന സിഗ്നൽ ഈ പറഞ്ഞിരിക്കുന്ന മെറ്റീരിയലിൻ്റെ മുകളിൽ സാമ്പിളിൻ്റെ മുകളിൽ ടച്ച് ചെയ്യുന്നുണ്ടെങ്കിലും it has to pass through all these Henderson lens and all those things. So while it passes through this one, if the surface of the specimen is close to the beam which is originated, that is the scanning beam, that is the signal beam which is originated, then of course this hitting of this particular material will be giving a very good resolution if this distance of the beam with the sample is adjusted in such a manner that there will be the beam which scans over the surface in order to get a very good resolution, and that will be even better than a low Z material that is usually having low Z material, uncoated material, low Z uncoated material ചെയ്യുന്നതിനേക്കാൾ നല്ല മികച്ച രീതിയിലുള്ള ഒരു ഒബ്സർവേഷൻ ആയിരിക്കും ബയോളജിക്കൽ സാമ്പിൾസ് നമുക്ക് കിട്ടുന്നുണ്ടാവുക അർത്ഥം. Then there are certain important terms. Actually, these are all something related to the some of the important parameters related to the SEM. That is the resolving power. What is meant by resolving power? Resolving power is defined as the ability to differentiate two lines or points in an object. So when the object or surface is scanned, whenever it is scanning, there are two. It should be capable to differentiate two lines or points in the object. So the resolving power actually gives it's actually an indicator that actually causes to differentiate one line with the other line or one point with the other point in the scanning of the surface. So resolving power is defined as the ability, that is actually the ability to differentiate two points or two lines in an object. The theoretical limit to an instrument's resolving power is determined by the wavelength of the electron beam used and the numerical aperture above the system. So that is the wavelength of the electron beam used and the numerical aperture above the system. So that I think you might have heard of this numerical aperture, all those things you might have heard, isn't it? Or you understand this one, if lambda is the wavelength and Na is the numerical aperture, then the resolving power R is given by, or resolving power of the instrument is given by R is equal to lambda by 2Na, where Na is the numerical aperture, it's a number. Okay, so lambda by 2Na, where lambda is the wavelength and Na is the numerical. Just to understand, that is actually, that's a parameter for a scanning electron microscope. Okay, the greater the resolving power, the smaller the minimum distance between two lines or points that can be distinguished. The greater, if the resolving power is very high, that is the ability to scan two adjacent lines are very high, then small distance between two lines point that can be distinguished very clearly. Okay, because the resolving power is very high means two distinct points can be very clearly distinguished. So that is the idea. Then, what are all the applications of SEM? Information that can be investigated using SEM are topographical information of the surface features of an object or how it looks can be understood. Then morphology can be understood. What is morphology? Morphology means the shape, size and arrangements of the particle making up the object that can be understood. Then composition, the elements and compounds of the sample with which it is composed of. The elements and compounds the sample is composed. So that composition can be understood. Then crystallographic information, that is very important. See this electron microscope actually gives a very good idea with regard to the surface and the elements or the materials which are used for preparing the sample or surface. So it gives topographical information, morphological information, shape, size, arrangements of particle, that composition, that the compounds through which the elements can be, or elemental compounds which have been used for the surface formation. Then crystallographic information, the arrangement of atoms in the specimen and the degree of order. Okay, so with this, I complete this particular session here. So you learned this one. I have given the notes in a very elaborate way. Just understand what is to be learned. And the specimen interaction is very important with regard to SCM tech. Understand that one very clearly. So wish you all good luck. Thank you. Thank you very much for listening my lecture session. Thank you.